All right. So I'd like to welcome everybody to this talk today at the MIDAS Symposium. We're delighted to have Chris Ray here from Stanford University. Before I turn it over to Chris, and in fact, even before I introduce him, I wanted to just give you a preview of a few upcoming talks next week. We have Ivana Seric, who is a data scientist with the Philadelphia 76ers and has been doing some really cool stuff over there. And then as you would have seen from the slide that just flashed by, we have Christian Nicolescu-Mizil and Thorsten Joachim coming up in the weeks thereafter. But let me just take a minute to tell you that Chris is a person who's been studying how to build practical machine learning systems and sort of making this something that, in my words, I don't know if this is how he would put it, makes it available to the masses because it doesn't require specialized, super expensive hardware that you can't afford, and it doesn't require super expensive training that most of us don't have. In that sense has done much more for bringing ML to all of us than perhaps even we realize. And for such reasons, among other things, he's been recognized as a MacArthur Fellow, the thing that's also known as the Genius Grant. And I'm not going to tell you about a long list of other awards that he's got, including the Kavli award from the NAS. And so just so I don't take up too much of Chris's time, I'm just going to turn it over to him. And Chris, excited to have you here and to look forward to your talk.
Thanks so much, Jag. I'm really excited to be here. This is actually my second MIDAS talk. My first one was in person, so I got to appreciate all the charms of Ann Arbor and walk around and have those coffees and those beers in person. So I look forward to hopefully being invited back. You don't have to have me talk, just to be able to hang out with some of you. I'm going to share my screen right now. And I think as Jag talks about, a lot of the work I'm describing, the motivation for it really was to try and bring a lot of machine learning to engineers and trying to make sure that those engineers had the tools to do their jobs. Didn't relegate it to the, kind of back end of, PhDs and other kind of labs. And so I'll talk a little bit today about both the systems that we've built and some of their underlying theory and this theory and system for weak supervision. So, you sometimes hear this phrase software 2.0, and probably you think about, when you hear that phrase, you think about these kind of really high-end applications, things like translation or medical imaging or robotics. And those are awesome applications. Those are great machine learning focused products that people are building. But underneath the covers, I claim there's something really interesting going on. And it was highlighted by Google in 2017 when they talked about how they replaced their old translation system with a new translation system that was 1,000-fold lines of code fewer. And so that level of code compression, because of these machine learning tools, was something that was really spectacular. And it was, code that, in fact, almost everybody could write. And this, to me, triggered a huge kind of revolution of productivity of how we kind of write research code and how we write production code as well. And you're starting to see that a lot of these problems that originally didn't have machine learning as an impact to them now are becoming machine learning first. Things like data cleaning, tuning your database, how you tune your network, and even how you build SAT solvers are getting machine learning infused in different components of it. So I got to spend a little bit of time in industry, and one of the things that I kind of picked up there is, why is this happening? Why is machine learning getting adopted by industry? And I think there's some software engineering reasons behind it that maybe aren't as well appreciated. So the first thing is that you can just build products faster. The speed at which you can build those high quality products is really, really amazing. A second issue is that deployment is a lot easier. It used to be that when you built a piece of software and had to go deploy it to your data center, you'd have to qualify it. You'd have to make sure it wouldn't blow up in some way. You know, C++ code, who knows what the heck is going on in there? There's Go, there's this huge mess of code. Now people are shipping models at an astonishingly fast rate because they have very regular runtimes. The way people write this code is data flow code, and that's something that just is incredible for you to be able to ship to the data center more efficiently. Now, there's also a host of challenges there with training, and this opens up a new wave of how you're going to train these systems. I won't talk about that today, but I'll point you at my collaborator, Kunle, who's the godfather of multi-core. He and I together are working on these projects about how you can build new styles of hardware that actually train natively machine learning systems dramatically faster. And he gave a beautiful NeurIPS keynote and an ISCA keynote about that. And this other bit that Jag hinted at, that you want to be able to have this ability that you don't need, you know, sometimes they're called ninjas, to be able to build and then maintain these systems over time. And since often we're going to these now self-supervised or weakly supervised systems, as I'll talk about, they often require lower maintenance overhead than the software 1.0 kinds of systems that they're very often replacing. So I think we're in the first innings of this game of how software kind of 2.0's view is changing pieces of engineering. And now, of course, there's still going to be standard classical code in these pipelines. It's not all machine learning. But this balance, I think we're really in the early innings of how you build this new generation of systems. And I think it's going to be a fairly profound change. So I'm really excited about it. Now, today I'm going to talk about a much more narrow topic than that, about what we do around, it's called training data. So at a high level, if you think about a machine learning application, there are really three components. There's a model, there's some training data, and there's some hardware. Now, the cloud has made it possible for hardware to be available like never before. You can go spin up a huge number of instances on effectively the latest and greatest hardware. So that's really exciting. Probably less well appreciated outside of core machine learning is that you can go and pip install, that is automatically download from the web, almost all the state-of-the-art models. And this wasn't true 5 or 6 years ago, but now, you know, a grad student in their lab or a developer who's working can download the latest and greatest in language modeling in a couple minutes. So those two things have really become commodities in a pretty fundamental way. But this third one, training data, seems to resist becoming a commodity. And in some ways, there's the thought that maybe it won't be, because the training data is how you program your application. It's where you describe actually what data you want to put into your system, what the task is that you're doing. Fundamentally, it's how you program your application. And so it's unlikely that's something that you're going to be able to just simply download from the web anytime soon. So what we started thinking about was this idea of, could we make creating training sets more like writing code and try and make it just a little bit less awful and a little bit less of a bottleneck than it is today. Now, when I teach 229, which is our machine learning course, our first content-filled lecture begins at the upper left corner of the whiteboard, where I start to write down, we have X and Y pairs. And those are our training set, our examples and the training data that comes with them. Where do those pairs come from? We never say. And it's as if they fall from the sky, from God herself, into your lap, and then machine learning begins. Now, anyone who's actually ever built a real system knows that that's not at all how the process actually works. In fact, training data usually comes from a dirty, messy process with multiple streams of data. So this is a picture of a sewer, and this is what it's more like. It's more like hanging out in the sewers, and it's like hanging out with Beyonce, building machine learning models. And so as I mentioned, our goal was relatively simple. We wanted to create a mathematical and system structure that could just make this messy process a little bit less awful. We're not going to solve it in any traditional sense, but we are going to try and understand this process and try and make it easier and faster, as I'll describe, for people to do. Now, I'll go one step beyond just saying that this is kind of, you know, a step on the process. And I'll even argue that in machine learning, if you've been paying attention, the height of machine learning where people really care is around supervision. And I'll argue that both in practical applications and even in machine learning research, modeling differences are now vastly overrated, whereas supervision differences are vastly underrated. Now, I like to work on real applications to hold my kind of feet to the fire. So I'll describe this in the context of this one application, but of course, it's a more general principle. So the application I want to talk about is this paper that appeared in Radiology, which is the flagship clinical journal. All the people in ties are physicians. The people without ties are computer scientists. Now, what we were looking at here was a problem that you've probably heard machine learning people get excited about. So we were looking at these radiographs. And it turns out people take these images and often they don't look at them. And the reason they don't look at them is, a variety of different reasons. They don't have the expertise. It's the person who has the expertise doesn't want to spend the time. Maybe there are cost reasons. So this seems like an awesome area for machine learning to have an impact because its bar is just, over not looking at the image at all. It's kind of a triaging system. So one of my postdocs, Jared, decided he was going to take a look at this question. And he basically wanted to say, are the state-of-the-art deep learning tools the right solution for this? Okay. Now, it turned out that when we started this was not an easy question at all. There was no benchmark data set for what we were after. This was a while back, 2017. The effects of data quality were completely unclear on the problem. There was no assessment of existing algorithms. So although there were many algorithms in the literature for various parts of the task, no one had actually compared them in their clinical relevance. And importantly, there was no feedback from the clinical community. So he spent a year really trying to answer this. He created a large data set of clinical labels. He evaluated the effect of label quality. And most importantly, he published it in a clinical journal. And we learned some really exciting lessons from this. The first lesson was that the models on this task, if you're kind of a machine learning nerd, you recognize these models. The lowest one is DenseNet, that's from Killian and Cornell. Has a great text accuracy, 91 here. That model at the top is an ancient model. This is something you could have comfortably trained 15 years ago. And the difference between them was only 2 or 3 points. What took a lot more time and effort was on label quality and quantity, and it impacted it much more than model choice. Now, at the end of the talk, I'm going to come back to some reasons we should both be worried by these numbers and some things that are quite optimistic about how these new models actually in some ways may be performing much better than the models that we had previously. But for now, I just want to dwell on this fact that all of our time wasn't on the modeling. It was really on preparing the data. Now, when I describe this, oftentimes people say, well, maybe that's just some simple application. Machine learning people, don't have these kind of problems. But if you look at our benchmarks, for example, this idea of data augmentation is absolutely critical. So augmentation is the idea that if I have an example that's a 6 and I want to generate more training data, I can rotate it a tiny bit, in either direction, and it remains a 6. I can blur it out and it remains a 6. It turns out that that augmentation layer is responsible for a huge gap. So this is kind of a weird metric to look at, but if you look at the top 10 differences in models, people are fighting over tenths of points. In contrast, if you remove augmentation from any of those models, they lose 10 points or more. So it's a huge orders of magnitude that's going into this area. And my pitch is, hey, we should just study what the heck is going on there. Okay. Now, it's even true that it pushes the state of the art. So the new methods of kind of pushing the state of the art, things like noisy teacher, are all about how you deal with training data. So one paper I'm super proud of, my student Alex and Henry wrote a while back in 2017, was this idea of just learning those augmentation policies. Should I blur the image and then rotate it? In what order? How often? It turns out that this kind of then decided, Google picked this up, did this auto augment thing, which was amazing. They pushed the state of the art in ImageNet. And actually just recently within this last year, we realized that very simple theoretically justified schemes can actually compete with these very, very heavy reinforcement learning and very sophisticated approaches and get the state of the art accuracy, which is super cool. A postdoc of mine, Sharon Lee, who's now going to be a faculty at Wisconsin, she had a model that was incredibly robust. If you know the issue about ImageNet v2, she's the only one that's above the trend line there when she was at Facebook. She took all of these images and trained it with a lot more data, but these images were only weakly labeled. And so she looked at how do you do that and how do you make these models more robust. So what I'm arguing is this is already really going on. Even in our research, we're bottlenecked on training data. So one thing I just want to highlight, I won't get to talk about data augmentation too much specifically, but we've been doing a lot of theory about it. Sharon wrote a nice blog post that is also on the Stanford AI blog post. And Sen and Hong Yang had a beautiful paper in ICML this year, which I described, where they follow on some work from some folks at Berkeley and figure out exactly how to set the statistics for how often you sample from these different augmentations. And we're able to set a new state of the art on CFAR 100, which is one of our benchmark image data sets. Okay, so please check that out. What I'm going to do, I'm going to spend a little bit of time zooming into a little bit of technical detail about training data for classification and labeling problems. And if you haven't thought about training data kind of creation problems before, I'll argue that the way we typically do it now is slow, expensive, and often static. So let me unpack what I mean by that. So traditionally, when you collect manual labels, your first label costs as much time as your last label. And what that means is people don't get kind of an economy of scale as they go through this process. They're still slow as they churn through each one of these steps. They're also quite expensive. We had a paper that was in Nature Communications this past year, and it was looking for rare abnormalities in video. And the problem is we didn't know the background incidence. We didn't know how many people actually had this abnormality. And it turned out it was about 0.5% of the population. So roughly speaking, you would have to have a radiologist or a cardiologist look at hundreds of images to find one. This would be untenably expensive to be able to conduct this study. A slightly more subtle one, but to me, which is kind of more conceptually significant, is that labels are static. If you label things as positive and negative, and then decide that your application actually needed positive, negative, and neutral, you have no choice but to go back and relabel all your data. In contrast, for things like code, we work in a fundamentally different way. We're able to refactor our code in some way and reuse most of it for the new task. We'd love to enable that kind of behavior for training data. So we started looking at one framework that would allow us to have some of these properties, just be a little bit better, as I said, than manual labels potentially in some cases. Okay. So these are these programmatic labels. It's one of many frameworks you could look at. They're going to be fast because you're going to write a program and then it's going to label huge tons of data for you. These little programs are going to be cheaper to run because they're going to run hopefully at the speed of AWS. That's going to be their dominating cost. And they're going to be dynamic. We're going to turn training data generation into more of a code and programming problem so we can reuse all the software goodness that we've known for the last couple of decades for building applications. Now, of course, this doesn't come for free. There's a massive trade-off here. And this is what we're going to seek to understand in our theoretical side, which is that these programmatic labels are noisy. Okay? They're lower quality. Worse, as we'll see, they may be correlated with one another. And we have to figure all that information out to be able to use them successfully. Okay? So we're going to look and drill into this framework a little bit more and see kind of how it works and what are the key technical challenges here. So the way we're going to frame this problem is that we're first going to look at an interface for generating training data via weak supervision. We're going to talk about an approach to learn the quality and the correlation of the sources. And then this is going to allow you to use any of those big deep learning models that we're so excited about that are hungry for labels. So Snorkel is just formalizing what people have done before. So if you look at this and say, well, I'm a machine learning person, I've been using lower quality label data forever, I would say exactly right. So for example, even since the 90s, Marty Hurst had these beautiful papers in pattern matching where she would basically go and heuristically label large things of text and then train a standard machine learning classifier. There's a technique called distance supervision, which is also quite widely used. Jurafsky and Mintz have a beautiful paper where you use a knowledge base to heuristically label a bunch of text. We talked about augmentation, topic modeling, third-party models, and crowdsourcing. The observation that was underneath our approach was that these techniques are used in ad hoc and usually isolated ways. And what we wanted to do was to be able to use all of them because we realized when we were building our models 5, 6, 7 years ago, these techniques and how we applied them were mattering much more than our models. And so that was a really interesting thing to try and figure out, how can we do some of these steps a little bit better? And so that's all that Snorkel was, an idea to replace those ad hoc things of weak supervision with a formal, unified, theoretically grounded approach for programmatic labeling. And that's kind of the progress that we set out there. Now, the folks who did the real work are here. Stephen Bach's now a professor at Brown. Alex is going to be a professor at the University of Washington starting next year. And all of them are part of actually a company that just spun out based on Snorkel. Let's look at an example of named entity recognition. Here we're going to try and understand, doctors and hospitals. A little bit artificial, but it'll help us get the basics of what's actually going on in these programmatic labels. So let's look at how weak supervision would handle this. Okay? So here we have a sentence, Dr. Bob Jones is a specialist, blah, 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 at a cardiology division at St. Francis. Okay? St. Francis is a hospital, kind of, any English language reader would be able to pick that out. So how do these labeling functions attack this problem? Well, one of them is just an existing off-the-shelf classifier. It's wrapped as a function. It takes this sentence in, and it votes person. Okay? Another classifier can look, another labeling function can look at the output of that classifier and then refine it in some way. And here it also erroneously votes person. And then this last heuristic is the distance supervision heuristic. It's going to go and look in our names of hospitals and say, ah, I've seen this hospital name before. I think this is actually a sentence that's talking about a hospital. Okay. So the problem is these sources are noisy. They're imperfectly accurate. In fact, the top two are right. They're obviously correlated. The second classifier uses the first one. And we somehow want to be able to denoise them and then be able to train our sophisticated downstream model. Okay. So this is the procedure. People will write down those functions. And then mathematically, we're going to treat it as a generative model, as a graphical model underneath the covers that combines all of those sources of information. If you're an expert, we're going to learn the structure and the weights of a latent graphical model. The reason it's latent is we don't get to observe the ground truth. And then we're going to put out training data, but now we're going to say how confident we are in every training point. And then we'll use that to train a resulting probabilistic model. So the key idea is that the training point is going to carry information about the accuracy, and no hand-labeled data will be necessary anywhere inside the pipeline. Okay. All right, so why might we go through this seemingly artificial two-stage process and do this? So let me describe kind of some of the reasons that we've seen and empirically why this kind of framework works or when it works. So the first reason is improved generalization. So one of the first things that we were after in our system was we noticed that when people would write those rules or do that distance supervision, they would tend to write very precise rules, but they didn't have a lot of recall. And we noticed that in most of our applications, you would get a huge recall bump from being able to first label the data and then use a sophisticated language model underneath. So for example, if you're looking for disease-causing chemicals and your labeling function referenced implicitly inside of it different phrases like treats, causes, induces, you would actually be able to get kind of near linguistic synonyms from the big deep model that was underneath the covers. And so even though your labeling function never mentioned these terms at all, the end model would be able to label them. And that's kind of why you would get this transfer and get this score increase over just using those kind of noisy rules by themselves. The other reason, which turned out to be more important in industry, is that you scale with the unlabeled data. So it turns out as you add in more unlabeled data without changing the labeling functions, it improves performance. And as we talked about before, you can actually refactor and take your labeling functions and apply them in new scenarios. And so the teams that were using labeling functions were just able to ship faster. The third reason is a little bit subtle, but it actually turned out to be more important than we thought. So imagine that going back to that radiograph example, you have that picture and you want to classify it as abnormal or not. It turns out that labeling those are very, very expensive, but there are tons of medical reports that are laying around about those images. So could you take all those labels and somehow transfer them from the text to the image? Now you may say, well, we'll just train a joint model across both. But the problem is you need a servable image model. That means you need something that just takes the image as input and then outputs a classification, abnormal or normal. In contrast, you can't have the report at that time. You could never feed it in because it's not servable because the report is written well after someone's diagnosed. So this ability to transfer from one modality to the other, this kind of knowledge transfer, that turned out to be a key property for a lot of where these things get used. I'll come back to this point in a little bit more detail later, but we've seen cases, and I'll explain one in detail, where people spent person years on the top part annotating images. And in only a few hours, they were able to bootstrap something that was nearly the same quality. And that kind of change of how you interact with your training data is what we're after. Okay? So just to recap, I hope I've at least expanded a little bit, some intuition about why manual labels are slow, expensive, and static, and how these programmatic labels are a little bit faster, potentially a little bit cheaper, and also dynamic. Now, if I'm telling you this, you may think, well, this sounds crazy and kooky. There's no way anyone's going to go for this. And probably, that's the reasonable bet, even odds on that. But shockingly, my students did a phenomenal job on this. And they actually got this thing used in this thing, Snorkel. They put it out there over the last couple of years. And this is an incomplete list. There are actually many, many more folks who are using this kind of system. Now, as Jag mentioned earlier, initially, we had targeted folks who were around campus to try and lower their barrier to entry to use the latest and greatest machine learning models that were out there. That was our goal. What was kind of shocking is the first place we were really publicly deployed was in Google Ads, far from the low resource environment that we were initially targeting. So one of those was a system which is called Snorkel Drybell. There have now been a couple papers about it. It's used inside Google Ads. Basically, it was this idea that they had tons of information laying around inside their ads pipeline for problems like fraud and other things. And they wanted to be able to bring it to bear to write a series of classifiers. And their engineers actually started to use the Snorkel Drybell. They have a ton of folks using this. And I advise you to check out the paper led by Stephen Bach. Interestingly, it's also used in a couple other products, maybe even things you've used. Things like Overton, which is a system that we built at Apple. The Gmail folks use something very, very similar in their software system. And Sahana just recently had this paper with some folks at YouTube. We're doing that kind of transferring from text to video kind of idea. That was an industrial paper this past year. This is a statement from some of our own work. This is actually done while I was at Apple. It's changed the use in real systems. So these teams, the resourcing here kind of refers to how many people were on the engineering team responsible for that product. The high resource people, they had lots of data going in. And you can see that this weak supervision kind of idea did have a pretty significant error reduction on their particular task, which are necessarily obfuscated since they're corporate tasks. You can see that the lower resource teams, who actually were shipping later, started to do a huge amount of work by just using weak supervision. So the point is, this isn't kind of a nice to have in some of these applications. For some applications, folks are really using this to go out and build industrial and scientific projects. Now, I mentioned Software 2.0, and I mentioned this very narrow slice. I want to call out a couple other things. There's this great system called Ludwig that came out of Piero, a guy who was at Uber and is now hanging out in our lab, which looks like a very nice declarative way to talk about your application at a high level. There's a lot more work to do here of making this pipeline kind of radically different when you build these new software systems. Andre Karpathy had a quite different take of what he thought Software 2.0 was, about how you debug these neural nets, but also very interesting and fascinating contribution to the area. And of course, none of this would be possible without these software frameworks that people are putting out now, PyTorch, JAX, and so on. These are things that simply didn't exist 5 years ago, and kind of the entire engineering landscape in this area has changed because of those tools. I won't talk about it in too much more detail here, but this is not something that's just limited to large companies. It's just kind of interesting because you may have interacted with those products, so maybe you would kind of think about how that would be useful. But these are also things that are getting into medical pipelines, radiology pipelines, all kinds of different places, and we're really, really excited about that. All right, so I want to give a little bit of methods, just a little bit of math, not too much, about how this thing actually works. And this is really due to Paroma. Fred, who I mentioned, is going to be at the University of Wisconsin, and Mei Chen, who is an absolutely stunningly brilliant second-year student. So in this pipeline, again, there's no hand-labeled data. The first paper was in 2016. Mei and Fred did some nice lecture notes last year about kind of how these basic systems work. You write these labeling functions. We represented those diverse source of weak supervision with those functions we saw earlier. And then we model the function's behavior and denoise them. And we're going to talk about how we can do anything here without ground truth labels. Like, it seems kind of mysterious, like, you don't need any label data here. And I'll explain to you why. The trick is quite obvious once you see it. So we're going to model this as a generative process. So intuitively, what's going to happen is every source of data is going to be a random variable. They're going to be correlated. So those are the lambda 1, lambda 2, lambda 3. Those are correlated with function 1, function 2, function 3 on the left-hand side. There's going to be a hidden ground truth variable y, which is the actual ground truth. And unfortunately, we never get to see that. And so what we need to do, if you're familiar with graphical models, is we need to learn the parameters of this model, the accuracies and the correlations, but without ever observing y, which is a latent variable. And we want to do this provably. So that's what we're after. So how could you possibly do this? Well, let's look at some intuition. So the point is we're rolling this up at the population level. That means we're seeing a source vote many, many times. So we see on the first point that the first source voted person, then person, the second source voted person, the third one voted hospital. On the second one, we see the votes again. And the key idea is we get to see where these sources overlap with each other, where they disagree, where they agree with one another. And it turns out that that's sufficient for us to be able to back out their accuracies and even their correlation structure. Digging into intuition, imagine I promised you that one of the sources was perfectly accurate. In that case, you could obviously estimate the accuracy of the rest of the sources. You simply count their accuracies relative to that ground truth. Now, if I told you it was 90% accurate, you could imagine how you would do that as well. The game is that we can find a solution where all of the constraints are satisfied, and in fact, estimate jointly all of the accuracies of the function simultaneously. That's where the math comes in. So how does it work? Well, just think about this as like kind of the standard covariance estimation problem. So if you have a graphical model that looks like that, this is the covariance. So an entry here, for example, corresponds to, I observe the expected value of lambda2 and lambda3 together, okay? Now, the problem in this covariance matrix is I don't observe y. If I did, I'd be done. Because if I took any lambda function, any one of those labeling functions, and saw how often it agreed with y, that would be a very, very simple way to be able to compute the accuracy. It's clearly directly related to each other. Okay? So somehow I want to figure out when I can kind of impute those red places from the green versions. And of course, I need some structure underneath the covers. I can't do this in general, right? Because those red numbers could basically be nearly anything as long as the matrix is positive semi-definite. So how do I do it? Well, let's imagine a case right now, okay? And this is where the art is, to try and figure out where the cases are. Let's imagine a relatively simple case and use a cute idea. So the idea is, let's imagine I knew how well I knew whether or not two functions were correlated or whether they were independent, given the label y. So if I knew the structure of the graph, then there's a beautiful fact. Okay? I don't need to know the structure, but just assume I know it for now. If there's no edge present between two labeling functions, then it turns out that the corresponding entry in the inverse covariance matrix is actually 0. Okay? So how do I use this? This at first doesn't seem very useful because I don't actually observe that thing directly. It turns out using the matrix inversion lemma, I can rewrite this entire covariance matrix, where there are the red entries I can't see, in terms of this green piece here, sigma O inverse, plus some low rank term. And I don't know what that low rank term is yet, but I know that it's only rank 1, so my life is good. So these things I observe, and these things are low rank. To get a rough sense of what they are, if you haven't seen this kind of inversion formula, basically if I had random noise, then zi would be equal to 0, and if zi were perfectly accurate, it would be exactly 1. Okay, so it's just a random variable that kind of corresponds to how accurate each of my m sources are. Here, 3 sources. All right. So now every place where I don't have a pair, when I observe an overlap, I can use that thing that I now have a 0. So I have a bunch of rank 1 parameters. I have some numbers, and now I've set them equal to each other so that whenever there's a 0 there. So as long as I have enough zeros, potentially I could solve this. So sigma, unfortunately, is full rank. It's not low rank. So it's not really a matrix completion problem. But intuitively, the key is that it's very, very close, because of the way these variables are, to something that's like identity plus something that's low rank. And this turns out to be the key to getting the right scaling. Okay. So just a couple of comments. Notice that there's a symmetry here. Z and minus Z are always solutions. So if I give you a solution Z, then minus Z is immediately a solution. What does this mean? Well, it means that we can't distinguish the case that all the labeling functions are positively correlated with the ground truth or exactly anti-correlated. So what we typically do to break this symmetry is that we say that on average, the labeling functions must be more correlated with the right class. And since we're using this in a programming model, that seems like a reasonable thing, right? But we have to break that symmetry. It's inside the model. Interestingly, in this case, it's the only one. When Zi is equal to 0, notice what happens. Then that constraint now becomes effectively a meaningless constraint, right? Because when Zi is equal to 0, then any Zj it appears with, I kind of get no information from it, okay? But this is the case, as I mentioned, when the underlying source is pure noise. And as a statistician, this should tell you right away, that's what I'm going to scale with respect to, how close I am to pure noise. And it turned out we worked very hard to get the right scaling in terms of that distance to pure noise. Now, it turns out for the real hardcore stats nerds, actually Michigan people here, this is actually, we should have just read Vershinin a little bit earlier, as many people have. If you're a theoretician, you've often bumped into this. Vershinin had a beautiful thing about effective rank. This turns out to be the right way to scale it. It's a continuous notion of rank, and this gives us exactly the right scaling for a host of these latent variable model estimation problems, and even some supervised cases too, which is pretty cool. Now, we didn't figure that out. We didn't read Vershinin early enough, so we wrote a bunch of papers. No, I'm just kidding. But one of the papers we wrote was in ICML 19, which is where we really started using this notion of effective rank to learn the optimal sparsity structure. So there you have to assume the model is reasonably sparse, and then we can recover it using a very expensive technique called a semi-definite program. We have fast method of moments estimators. If you're a machine learning nerd, you'll appreciate these. They're blazingly fast, but they can have a standing bias. And this is a standard problem with tensor methods in general. And this got Mei very interested in this problem. And she started looking at bias variance decompositions for method of moments. And now we can correct that bias and at least understand what its trade-offs are, which is super cool. And there even are some connections to causal inference with which Charles and other folks did in this instrumental variable method. So what I want to point out here is, even though I'm showing you this thing that hopefully looks relatively straightforward and simple, it's kind of a kernel that lets you attack a host of these kind of weak data problems that we think are really interesting and we've been working on. Okay. Now, you could ask some other questions here, like, do we recover the optimal solution? One very thing I'll point out is, yes, you can get generalization results. You have to assume something. The thing you have to assume is that your labeling functions cover the space. If you assume you had an IID sampler of the space, then you automatically assume you have coverage. But for labeling functions, I don't think it's that obvious. So if you are willing to make the assumption, then you get generalization at the same rates. And actually, we have a new paper coming out that gets these constants all right. Basically says how many points are weak points worth compared to traditional supervised points. And it turns out it's a constant. And that's pretty interesting, modulo this coverage issue. It works well on benchmarks, but this doesn't matter as much as it works well when people use it. Okay. So let's go back to radiology and see a place where people are using it. All right, so here we're exactly in that scenario I highlighted earlier. We have an image, we want to train a classifier for it. We have a bunch of text reports as well. Can we leverage data programming across modalities to make this a little bit easier? Recall, this thing is servable. We want to be able to take in an image without any text and produce a diagnosis. And the top is not servable. That's text that's written later. So we want to be able to use that to get labels retrospectively. So these folks really did this. This is a person month spent labeling radiographs. This is the accuracy you get. They then spent person years. This is the accuracy you get. It's kind of the standard curves. Then Jared, who's absolutely brilliant, basically went and hung out across the street. And he spent about 8 hours writing about 20 labeling functions. And then he let it run for the weekend, basically. And that's where he got in days of total compute time. Okay. Now, you could very well look at that and say, well, it's slightly worse than the years. Okay. And I say, okay, it's true. But that, I think, misses the point. The point here is that this just took a little bit of iteration, and then you knew there was signal present. It didn't require any hand labeled data to get there. And so one of the places that we do see this used now increasingly is as the first cut to make sure, is there should I invest in more training data or not? And in fact, as I mentioned in industry, it's the same thing. The reason some teams are using it, say inside Google, from what we've learned, is that they see, oh, I can ship my product before the other team has even started or finished collecting their training data. That's a pretty interesting split in how you interact with this. Of course, you have to validate your system using hand-tuned data. That's what we've been up to so far. But this is a pretty interesting way to approach the problem. Doesn't work everywhere, not saying it does, but when it does, hopefully it's a powerful paradigm to kind of change how people are building these systems. Now, when you look at this, one thing I want to be very clear is, because it's kind of a weird positioning and story, I kind of go through it independently, but all of this was inspired by so many folks. So many pieces of work are here. This is a very incomplete list. We try to maintain a nearly complete list on our blog. Please send us updates. We absolutely love it. This is an area that's been really fascinating to work in and learn of connections to tons of other areas. But there's just so much going on that's related to learning with labeled data. It's really a core problem in machine learning. And I think hopefully I've convinced you also in how we build systems. Now, I wanted to conclude my talk, just use the last 10 or 15 minutes on something different that's related to this problem of what these new systems kind of crop up with. And the idea that they have these kind of new abstractions that are underneath the covers that we're building with, picking up on this theme, and they introduce new problems. And I'm not sure totally how to solve them, but so I want to call out the problems because I think they're very interesting and also potentially important. But also tell you that there's some really fascinating things going on under the covers that I found, and again, Jared's work is featured here. So these two folks here are physicians on the left, Gustavo and Luke. They're physicians and ML people, and we wrote this paper together, a series of papers together. The first one called Hidden Stratification Causes Clinically Meaningful Failures in Machine Learning for Medical Imaging. And I definitely advise you to check it out on the blog. I learned a lot by this work. They really educated me about this. So what's the problem? So probably weirdly, like, why is he showing me these weird eyes? Well, this line of work actually started for me in a kind of strange way. Okay. So, if you think about machine learning, the reason I love it, and the reason, as I'll argue, most people love it, is that these models pick out unintended signals. If you can write perfect Python code to do a task, do that. Don't machine learn it, okay? It's feasible to do. If there's no possible way to write down any specification for your task, also not clear that you should use machine learning to do it. What we love are the fact that we can write these programs that kind of incompletely sketch the solution, and the machine learning kind of fills in the detail. And necessarily that has to pick out signals that weren't totally obvious to us as we were writing them. Okay? Now these new generation of deep models, they pick out even more unintended signals than we did in the last generation. And in some ways, that's why we're so excited by what they do, that they learn and build these kinds of systems. Now, there was a series of papers that I didn't really follow, and I only kind of read about this on arXiv. And there were basically folks, what they were looking at is they were looking at irises, and they were trying to classify them as genders. Is this a man or is this a woman? By looking at a picture of just the eyes. And they couldn't figure out, so apparently people were trying these models and they didn't generalize to new sets. So they're wondering why is it working sometimes and not others? And there was a wonderful paper that described this that said, gender from iris or gender from mascara. And the idea was that the models underneath the covers were not picking out anything causally related to gender and irises. They were actually picking out whether or not the person was wearing mascara. Now, that's an unintended signal. It's kind of awesome that the machine learning model picked it out, but it's also equal parts terrifying that that's actually what it was doing. So we started to ask this question, say 2016 or 17, do we know how well these models are performing? So go back to that slide I showed you earlier. Are we sure that those 2 or 3 points of difference are really causal? Are they anti-causal? Could they be picking up on something we don't want the models to pick up on at all? Kind of a terrifying thought. Now, you may say, oh, it's just the eyes thing, it's the iris thing, maybe if, real, no true Scotsman would make that error. So, well, I don't know. So we started looking into this, and here's an example with surgical marks, very famous set of work in this area, taking deep learning and trying to apply it to things like dermatology. So here's a picture of a lesion, and at the bottom here, you can see the heat map. And the heat map, what it's looking at is saying, where is the machine learning model focused? Where is the salient pieces that it's pulling out for classification? Here's another image. Now you look at the heat map, it's pulling out these 2 purple dots. But those dots indicate you're going for surgery. That means that it's cancerous. You would not want to be diagnosed by a machine that was relying on this feature, because it would mean that you were being diagnosed only if you had already been diagnosed. Okay, so maybe it pops up there. Here's another example. Pneumonia detection in all the newspapers, right? Online everyone was talking about. You have these images. I can't tell the difference between these 2 images. My postdoc has shown me these images. You could switch them, permute them. I would be oblivious. No idea what the difference between these 2 images are. Now you're trying to determine whether someone has water in their lungs, pneumonia. Okay? When they ran this test, like pneumothorax detection, had a huge AUC, which is apparently superhuman. Super exciting result. The problem is the image on the left doesn't have a drain. The image on the right does have a drain. A drain indicates that you've already been treated for pneumonia, similar to this anti-causal thing we saw with the purple dots. It turned out 1/3 of the images in the test set actually had a drain. If you remove them, the progress is not superhuman anymore. It's actually, as Ben Reck tweeted out, it's at the level of a first-year resident, okay? Below the level of first-year resident. Okay? So my point is, these are serious errors that are happening in our training data. What's going on here? So we started thinking about this. We don't have all the answers. To be very clear, I have and will make much worse errors than those things. I'm not saying that those errors were wrong, but we don't have a theory to talk about what's going on here. So classically, you'd never write a feature that said, if I see a drain, then classify as pneumonia. If there's a purple dot, then classify as cancer. The reason it's happening is, in my estimation, is you're at a higher level of abstraction. And when you introduce a higher level of abstraction, new styles of bugs creep in, always, in every kind of software system. And that means new bugs that we have to address and figure out tools to help us identify. Now there's a lot of interest in what they call adversarial attacks, but these are only adversarial attacks if you're your own worst enemy. These are accidental things. We don't even have a theory to be robust against these. And if you run the adversarial methods on them, they don't work, honestly. So one of the things that we identified, one case that we identified here, is that what was going on is in the abnormal case, there were actually many different labels. So imagine here that you had pneumonia and there were two cases. You had pneumonia and you were treated, so you had a drain, and you had pneumonia and you were not treated. That kind of should have been the right label, at least one way to conceptualize the problem. And so there are these many unlabeled strata. So all you saw was abnormal. You didn't see either of the pieces. So could we develop a theory and techniques to handle this case of hidden stratification? So this is a paper that just appeared in this NeurIPS. For this problem, the summary here, which is kind of amazing, is those models that I said, do we know if they're doing any better? It turned out that those models, like those sort of dense net Killian's model that had these richer featurizations, interestingly, in their representations, sometimes, and we don't understand when, we have some hypotheses as to when, they actually separated out the classes. So even though they weren't labeled, it actually forced those two underlying classes, those abnormal with drain and without drain, apart. And so we could amplify the fact that those hidden labels were there without needing to know that they were present by augmenting the underlying structure. And this allowed us to improve our accuracy on those worst performing subclasses by a pretty dramatic amount. And so we identified kind of simple assumptions when we could show that we could fix the error, meaning we would get back to the same generalization that we had hoped before. But we still have a very preliminary understanding of how this happens. And we're just calling out that there's actually interesting both theory and methods to do here to try and debug some of these errors that we're seeing in the wild. Oops. All right. So I think there was a question. Let me see. Oh, how do you analyze and generate those heat maps for pixel importances? Great question. There's a bunch of different methods that are out there, but these are all standard. These are not ours. These are things like GradCam and other things that are in the literature. And there's a great publication called Distill and Gradient, where people describe various different visualizations for what your neural nets are doing. Really wonderful question. Yeah, please definitely feel free to ask more questions. I prefer to answer questions. Okay, so the last thing I want to mention is kind of one little tidbit I'll leave you with is what are our future directions? Okay. And we're looking at problems, modalities, and different kinds of supervision. Even weaker forms of supervision is what we're after now. So the analogy that is helpful to frame one part of our group's direction is the following. You can think about kind of this analogy with machine code. Traditional supervision is kind of like the zeros and ones of binary code. It's really like the bit banging that you would do on old hardware before you had an assembler. Labeling functions are coded, okay? And this is one of the things we've been looking at. They're kind of like an assembly language. They're still not very rich. They just kind of allow you to have kind of macros to slot around the same instructions you're using time and again and get a little bit of this reuse. And they're a convenient framework to analyze what the heck is going on in some cases, right? That's what the theory is for. When can we trust these things, when not? You can also imagine building labeling functions with more advanced primitives, where you start to compose software libraries and think about these. These are like high-level languages. We're starting to go in some of those directions over the last couple of years. You can also imagine that these labeling functions are coming directly from language. So people type natural language, and then they use that to instantiate programs, which is super interesting, right? I mean, to me, that there's this whole thing, like, for example, the way people are using GPT-3, you kind of feel there's this natural way you're prompting and teaching the system. That feel is something we've been thinking about for a while, but the way they're doing it seems really exciting to me. So that's kind of a direction that we'd love to figure out how to go and be more systematic about. And another entire direction inside the lab is what we call observational supervision. And the idea here is that we want to instrument people in the way that they're interacting with their environment. So a radiologist, we may instrument their software. We may have them wear glasses that or have eye trackers in them, but something that's kind of non-obtrusive, where we're looking at huge amounts of data. The signal is relatively weak, and we can pull out some information from it. Something that my PhD student, jointly advised with Daniel Rubin, a radiologist named Khalid, is working on, and we're really excited about to try and understand, what are the weakest signals that we can learn from, and how does it work? Now, much more important than my view of the world I don't really get a vote in what the lab does. I like to think I do, and they do a pretty good job of telling me that I do and fooling me. But really the folks who get a vote in the lab are the postdocs and the graduate students who actually do the work. And they wrote up in February kind of a list of, hey, here's some things we learned, here's some things we're excited about. And they'll probably do another one. And so their ideas are always better than mine. So I would definitely go straight to the source here and kind of check out what those folks are up to. Laurel Orr and Dan Fu wrote this thing. Laurel Orr will be on the market next year. Hopefully people will be hiring. So in conclusion, what did I describe for you? I described this framework called Snorkel, which allows you to train relatively sophisticated machine learning models, but has this idea that you're using kind of software ideas to be able to build these next generation of models. My students all hate the phrase software 2.0, but I like it, so I still use it. I showed you there's one nugget. There's actually, to me, the thing that's interesting is there's a really rich theory here that gives you kind of a different take on all kinds of classical problems in statistics. Structuring, estimation problems, problems of miscalibration, misspecification, all come up when you're in this latent variable framework. In some cases, our techniques have even been able to contribute back to the kind of more classical statistical literature, which is really exciting here. And it is fun when you go into these theoretical problems. But at least I hope to tell you that this isn't just kind of a direction that's just kind of a high level or how you interact. I think it has really foundational implications, or there are foundational problems that are raised, questions that are raised by this approach. So we're really excited to work on those. And I still don't know how to articulate this totally in a way that makes me happy, but this idea that you should focus on supervision really changes how and what you build. And Snorkel was one incarnation of that, which we're really excited about. But how you think about how these systems are put together, when you think that maybe models are overpriced, but their description of the model and the managing them and how you put them together is underpriced, that just changes where you think there's an opportunity to really accelerate the way people are using machine learning. Now, to be clear, we still do a lot of research on models. There's a lot of really, really exciting work there, but this worldview that's a little bit different, I think is worth exploring. And that's really kind of the thing that I hope you take away from this talk. Thank you so much for your time and attention. I really appreciate the opportunity to hang out with you. And I will say that I did recently have a daughter, and someone actually sent me Zingerman, so I am very happy about that, and I will love you forever for that. Thanks so much.
Thank you, Chris. There are a whole bunch of questions, mostly in the Q&A, but there's one in the chat as well. Do you have an idea or estimate of how much bias propagates in training data and the trained models that use weak supervision systems like Snorkel?
Wonderful question. Yeah, so in one very overly harsh way to describe what we've built is like a bias generating machine, where the biases that are in the head of the developer are injected in rapid fashion inside the data. And that's one of the things we were most terrified about. So a couple of things. One thing that mitigates that in a practical sense is that, if you don't want to be biased, this gives you a tool to describe the lineage of your training process and lets you iterate on it. So just as a practical matter, you can start to remove some of that bias in a systematic way and review what goes in and what goes out in a way you really can't feasibly do with crowd workers or contract workers. In a more mathematical sense, there's actually a way that you can quantify this directly of how using weak supervision actually does introduce a standing bias. And that's something that we're really excited about. We have a paper. If you're interested, there's a draft. We'll probably post the draft actually next week. But send me about that on the more mathematical question of how does the misspecification of error actually get introduced? If your model is well specified, which is the standard statistical assumption, actually there's no bias in the formal mathematical sense. When it is misspecified, there's a latent bias. We can quantify it and even remove it. And then the last bit is more the heuristic notion or colloquial notion of bias. That is a serious problem when you do this, but at least you have kind of a specification that's possibly reviewable to remove bias. And I'll point out one last thing, which is that hidden stratification has a lot of connections into the fairness literature as well, because it deals with disparate impacts on subgroups. And so hopefully these tools can kind of all get together. And we're certainly informed by that literature. It's a really wonderful question. Awesome. Oh yeah, so Jeff Fessler asked a question. Could your weak labelers be based on essentially random linear combinations of the data, or do they need to be reasonable handcrafted models? Interesting, fantastic question here. And so I think as you look through this, mathematically the property that you need is twofold. On average, this is the weakest conditions we know. Maybe there are weaker ones. On average, the labelers have to be correlated with their target class. So basically, if you think about their accuracy and I were to average them, assuming they vote everywhere, just to make it easier to say, their accuracy should be 50%, okay? Greater than 50%, strictly greater than 50%. You scale poorly, so imagine they're all 50 plus epsilon. Then the question is, how do you scale in that epsilon? And we worked hard there, and you can get kind of, depending on the situation, anywhere from quartic to quadratic, which is kind of what you would expect in various different situations. If, however, all of the labelers are in cahoots, they're all correlated, like they all have access to the same random source, there's nothing that can be done, meaning you can't learn absolutely anything there. Now, there was a really fascinating paper that just came out from some theory folks I was talking to last week, where they started to quantify, okay, maybe you're only making errors with those noisy labelers closer to the boundary, so you don't care about them for classification. In that case, maybe more can be said. You can get rid of some of these restrictions. And they wrote a series of papers. These are some folks from Duke. Ranga and other folks wrote about those, which are super interesting ideas. Now, for regression problems, there's a whole host of issues about, what actually are you doing? We haven't worked too much on regression problems overall. There are a couple of problems there. I would say engineers' intuition, to kind of conclude this argument, given our experience, mathematically it's fine if you're getting close to 0.5 and all the rest, but engineers' intuition, if you don't have a couple of sources that are kind of 60, 70% accurate, kind of in that easy regime, it's not clear how much getting a fine notion of accuracy really, really helps you in that situation. So we wrote this study, and basically what happens is, if all your labeling functions are super accurate, then you don't need the framework. You just take majority vote, basically. If you have them be completely independent and you have tons of them, you can't get much material advantage over majority vote, but you should certainly never do worse. If they're all dancing around this 0.5, mathematically you can do better and scale in a better way than kind of naive approaches, but application-wise, it's not very useful. It's like you're still producing data that is 50 plus epsilon 2 epsilon accuracy instead of epsilon squared accuracy. It's not materially meaningful to people. So you kind of have to have something that's in the 70 to 80% range. I don't have a great paper to point you to on regression per se, but people are using it there, and happy to find a pointer offline. Thanks for the great question, Jeff. Cool. Are there other questions that are there? Awesome. I think that about does it. Are there any last questions? I thank you so much for the great questions and the great visit today virtually. It was really a blast.
Thank you very much, Chris. That was a fantastic talk, and look forward to having you visit again.
Sounds good. I look forward to it. See you all.
Take care. Bye-bye, and see everybody.